All right. So we are looking at the reaction quotient, which is similar but different than the equilibrium constant. Even though concentrations are not equal at equilibrium, there is a relationship between them. So this is called the law of mass action or equilibrium expression. This is a chemical equation between the concentrations and reactants, concentrations of reactants and products. If you've done any of these things in the past, this should look fairly familiar. So we have a chemical equation, a general. Again, sometimes this might have one product, might have only one reactant, doesn't matter what it is. But this gives the relationship that the lowercase letters represent coefficients of the balanced chemical equation. And it's always products over reactants. K is called the equilibrium constant. There is no unit. It does have meaning, but it has no units. Even though these don't necessarily cancel out, don't worry about that happening. So we see the products on top. These are the concentrations or molarities. Remember that these can be moles per liters of gases. They can be moles of liters of solutions. Keep in mind, things that have concentration are going to be found here. And that these coefficients could be the powers of these coefficients you have here. All right, so this should look familiar if you've seen this before. Now, how are you writing these ones? You see all of these have gases. Gases all have a concentration. Gases all have concentrations. We have the products, NO2 and O2, and we can see their coefficients are their powers. If it's just one, it's just one. And this is showing a relationship of how these come together to give this meaning of what this equilibrium constant will be. So expression, equilibrium constant. Now, when we talk about heterogeneous equilibria, concentrations of pure solids and pure liquids don't change during the course of the reaction. And think about that, moles per liter. If the solid dissolved, let's say in an equilibrium expression, the solid dissolved in a solution, but still some left over, the moles went down, but so did the volume. And because they're going to go down equally due to its density, therefore its concentration does not change. Same with pure liquids. They're not included in the equilibrium constant expression. So we have the chemical reaction. However, you see the expression does not contain anything that's a liquid or a solid. Keep that in mind. So if we have the same amount of CO2 and CO in equilibrium, and that the carbon dioxide and carbon are going to produce carbon monoxide, the idea is that we have the same concentrations at equilibrium no matter how much carbon is present. It's not a focus of the carbon. It doesn't change it at all. So therefore, the amount of carbon has no effect on the position of equilibrium. It's not going to be shifted one way or another or favored one way or another. Now, thinking about in gas form, sometimes you can use concentration, moles per liter. I mean, you can do a molarity pretty simply of a gas, but often it's going to be proportional to its partial pressure. So therefore, K can be expressed as a ratio of the partial pressures of the gases. We often have a lot of expressions that are gas form, and that you can see that this is the equilibrium constant with concentration. There's equal one for pressure. Same setup, same ideas. We will not have to convert one to the other. They do have slightly different meanings or different values, but the idea is that we have one method for concentration and one method for pressures. Now, so far you've seen what are at equilibrium, where changes are not happening. Concentrations are not changing. The reaction quotient, similar but different. Okay? This is when it's not at equilibrium. So the reaction quotient is used. That's a very generic term, right? It's a quotient, that's like division, of the reaction. So what is the same? All math operations, expressions, and meanings of magnitude. Okay? We'll get deeper into what these are and what they can signify, but mathematically, what they mean and what we do, like our setups here, are all mathematically the same. Only we call it Q. forward and backward reactions are happening at the same time, not necessarily at the same rates. Okay, keep that in mind. C is concentration, P is pressure. This does not include the species of solids and liquids since they have independent concentrations. So all that's the same. How is it different? We get some different symbols, Q's instead of K's. This is for any position that's not at equilibrium, not. So there's going to be questions totally about equilibrium and then questions not at equilibrium. And based upon where they're at, you're going to have to make judgment of, is it going towards the reactants, towards the products? How can we get it to shift? The rates of forward and reverse are not at the same, okay? Likewise, when we've talked about things happening and getting to equilibrium, they're not there yet, so these are not the same yet. Magnitude indicates the direction the once at equilibrium system will shift back. So when we see these values, and this will come up in later units, that'll help us tell, are we already past equilibrium and need to go from products to make more reactants? Or are we not yet at equilibrium? We still are making reactants approaching equilibrium. Okay, so that's what is different about it. It's a little complicated because it's different. We put a lot of focus on equilibrium. And so when we talk about not at equilibrium, often I always think of, why don't we just wait? We'll get there. All right, but this is what we're looking at and to talk about it as approaching equilibrium, or it went past and has not yet come to equilibrium when we think of the concentrations being constant and rates being the same. All right, I'll catch you about 7.4 coming up. Take care. Bye-bye.